Okay, I just would like to start by saying thank you to Selman for relinquishing some of his time. And thank you to all of the organizers for a spectacular workshop. It's yet another one that these are always so much fun in the summer. So it's a good end to the summer and start of the semester. Okay, so my goal here is to talk on handle-body structures of rational balls. And what I really want to do is I want to address a question of Kodakami and Yamada about the handle-body decompositions of certain rational balls involved in generalized rational blowdowns. So that's sort of the goal of the talk. We'll see. We'll start by talking about some Lin spaces and remind ourselves about rational blowdowns. So if we fix integers p and q co-prime, we'll assume p is larger than q, and we'll assume they're positive. Then the Lin space LP squared PQ minus 1 bounds two special four manifolds. The first one is CPQ, which is given as the boundary of a linear plumbing, where we consider a continued fraction expansion for the fraction negative p squared over PQ minus 1. And to specify CPQ uniquely, we'll require that all of these CIs are strictly less than negative 1. And then we can form this manifold here, and it's known that the boundary, in fact, it's easy to see that the boundary is the Lin space LP squared PQ minus 1. As we go forward in this talk, we'll encounter other linear plumbings. It's worth saying that at no point are we going to be looking at CPQ again. So I say this, I will have Euler classes that are strictly positive. So, but for the construction of rational blowdowns, we would require this. So according to this continued fraction, we can also construct a two-bridge knot, which is known that if we look at the twofold branched cover of S3 branched over that two-bridge knot, we'll get the Lin space again. And so for this particular choice of fraction, it's a result of Casson and Hare that this is actually a slice knot, and that if we look at the twofold branched cover of the four ball branched over the slice disk, we'll get a rational ball, whose boundary is also LP squared PQ minus 1. So what we can do is if we can find this configuration of spheres inside of a four manifold X, we can remove a neighborhood of it. The boundary will be a Lin space. And we can glue back this manifold BPQ. And the result will be the rationally blown down manifold along CPQ. So obviously this greatly changes the topology. Ron Fintischel and Ron Stern originally studied this for CP1 and BP1, and then Jean-Yul Park went and studied it for CPQ and BPQ in general. And what they were really interested in is the effect that this has on the Seiberg-Witten invariance. And so it has predictable effect there. So it's an interesting construction for developing exotic structures on four manifolds. But since I'm stealing Selman's time, I should talk about handlebodies. So the question here at hand is, what is an appropriate handlebody for this manifold BPQ? And so if we look in the literature, there's a number of possible decompositions. So the first one that I'll mention is you can find in a paper of Lakili and Maidansky, and they mention that this may have been known previously, so I'm afraid to say that it's theirs, but it's where I've seen it. And so if we consider a single one handle and we attach a two handle with framing PQ minus 1 along a knot that traverses the one handle P times, where we take Q strands, put a full twist, and take them over the remaining P minus Q strands. So from this description, it's obvious that this is a rational homology ball. It's maybe less obvious, but it's true that the boundary of this manifold is LP squared PQ minus 1. We'll see at least a proof of that today. And in fact, what we can do, what Lakili and Maidansky were interested in was actually the symplectic topology of these rational balls. And so they developed them they developed this Handle decomposition as a Stein domain. And so if we want to get to the picture that's actually in their paper, what we need to do is slide these Q strands on the left under the one handle. And in doing so, we'll turn all of these crossings in the two handle attachment to negative ones. And then if we put it in Legendrian, if we isotope it to be a Legendrian attachment, we can see that this is a Stein handle. And through their construction, they're able to show that, in fact, the induced contact structure on the boundary agrees with the universally tight contact structure on the lens space. That is, the contact structure that the lens space inherits from the tight contact structure of S3 given the quotient, under the quotient. And so that's very good because those are well understood. Symplectic fillings of those are well understood by Liska. So this is a good fact to have around. And just for posterity, there's a nice symmetry here that BPQ is diffeomorphic to BP, P minus Q. And how do we do that? Well, we just twist the one handle. So we can, wrong button. We can move this positive twisting to this band by twisting the one handle, and the framing changes accordingly. Okay. So that's great. This seems to answer the question, but then previous to this, there's another paper of Yamada's that introduces a rational ball bounding the lens space. And so Yamada's construction is as follows. If we pick two integers m and n, again co-prime and positive, this time we don't care whether one's larger than the other. And we again attach a single two handle to a one handle along a curve with framing now mn, where we attach it, we run it around the one handle m plus n times. We take m of the strands and run them positively over or right-handedly over the remaining n strands. And so what first of all, it's obvious this is a rational ball. The important thing that Yamada proves is that there exist integers p and q, so that this boundary is, in fact, that lens space. So the way he cooks these integers up is he uses the Euclidean algorithm in a sort of constructive manner. We'll give a definition of how to cook up these integers p and q in a little while. So what's not clear is whether or not this is the same manifold as this one. And so this is the question that's at hand. Again, there is a symmetry here that we'll certainly take advantage of. This symmetry is even easier. AMN is the same as ANM. Just flip the picture over. And just literally flip the picture over. Okay, so if we pick M and N and P and Q in such a way that their boundaries coincide, we can ask the question, are these two manifolds diffeomorphic? And maybe even before trying to answer that, a very related question is to ask, can we put a Stein structure on AMN? So, certainly if we can do that and that Stein structure fills the standard contact structure, then we're in great shape. But so this is the first question. I don't know why I keep doing that. This is the first question that we would like to think about. So we come to the first theorem, which is an affirmative answer for that if we pick coprime m and n, then every one of these AMNs admits a Stein structure. And the nice thing about a proof like this is that it's constructive. We can just do it. So based on that symmetry, I can assume that n is larger than m. And then what I'll do is I'll write n as m times some quotient plus a remainder. And now I'll open up this handlebody picture into two-ball notation. And what I've done here is I've written these m strands, and then I've exaggerated the n strands as a number of copies of m strands plus a remainder term. And so this knot here is Legendrian. If we look at this, we see that the Thurston-Benneken framing agrees with the Seifert framing, so this is not a Stein handle attachment. So now we stare at this for a while and try and decide what to do with it. And we do the same sort of trick that was done with BPQ. We slide something under the one handle in an effort to rectify this. So what we'll do is we'll slide this bottom strand here under the one handle. That'll, of course, change the framing. So we have to be very careful with that. And now, again, we have a new handle or new attachment circle that we're looking at. And the only issue that we have here is I haven't drawn it Legendrian, but we can see what we would need to do to make this Legendrian. We would need a cusp here, and we need a cusp there. And if we actually calculate out the Thurston-Benneken framing, we haven't done anything useful. So this is sort of too bad. The one good thing, though, is if we could get rid of one of these cusps, we'd be in great shape without affecting the writhe. So that's going to be our goal. And the way that we'll do that is we'll consider this strand that goes behind the rest of the braid here. And I'll call that the bad strand just for notation. And what I want to do is I want to try and trade negative crossings in the bad strand with positive crossings elsewhere through an isotopy. And the way I'm going to do that is I'm just going to start wrapping this strand around the one handle. So if I drag this strand over and around the one handle once, I get something like this. And then I can do this again, sigma 0 minus 1 more times. Each time I do this, things get a little better. This bad strand keeps getting smaller in the sense that it involves less negative crossings. And every time, if we were to try and put this in Legendrian position again, we would again come up with Thurston-Benneken framing agreeing with Seifert framing. We're still not quite there. The one place we would be there right now is if our remainder term was exactly 1. Then in fact I could just put a single cusp here, and if I calculate the Thurston-Benneken framing, it would be a Stein attachment. So already, if n mod m is 1, we'd be Stein. If it's not, we're still okay. What we can actually do is we can start pushing this over the one handle. It'll come here, and then we can run it down and then back up each one of these and bring it all the way to here. So now we have to run it many, many times to try and fix this. And if we do that, you can convince yourself that it will end up here. And now in this case, what we've got is now that remainder term could be 2 if we pull it over here. And then we can do this trick again and again and again. And if we do this enough times, what we'll actually be able to do is move this strand all the way down here, as so. And so we end up getting ourselves a Stein attachment. So here is the Stein structure on Yamada's manifold AMN. So this is great. This means that, or bad, depending on how you want to view it. If you'd like AMN and BPQ to be different, then this is maybe not so great. But since they're going to be the same, it is great. And so what we want to do now is what we'd like to know is the induced contact structure also the standard contact structure on the lens space. And so to do that, what we're going to need is we're going to need a way to correlate these two contact structures, to compare them against each other. So we need maps from the boundary. So at this point, we run off and we start producing boundary diffeomorphisms. And so I should say before I get to the theorem that these kinds of diffeomorphisms were known. I mean, Yamada has, in his construction of AMN, he constructs a diffeomorphism to CPQ, in fact. And similar ones should exist for BPQ. These ones are maybe defined slightly differently, but nonetheless, it's not surprising that we should have a diffeomorphism here. So the theorem that we have here is that there exists a diffeomorphism F from the boundary of BPQ to the boundary of AMN. And of course, there's no new content there, but then the interesting piece here is that we can arrange it so that F carries the belt sphere here of the single two-handle in BPQ to an unknot in AMN. And in fact, we can further arrange it. I haven't written it here, but we can arrange it so that if we look at a zero-frame push-off, it takes it to a zero-frame push-off over here. And so this is great, because what we'll find is that if we carve out the disk that gamma bounds in AMN, we'll get S1 cross B3. And this is actually enough to use a trick of Selman's to extend this to a diffeomorphism. So in fact, what we have here is that this map F extends to a diffeomorphism between these. So in an effort to answer this question using Stein structures, we actually can get one just through the Handlebody theory. So the proof of this is carving. And so how does this go? Well, we have this boundary diffeomorphism. And what we want to do is we want to first extend it into a collar neighborhood. And then we can, because of the way that this diffeomorphism behaves with respect to mu1 and f of mu1, we can extend across the co-core and the image of the co-core. And what we're left with then is a map from the boundary of S1 cross B3 to itself. And so now it's a question of, can we extend across that? And that's just a matter of checking whether or not this diffeomorphism intertwines the spin structures. And so we can do that because this diffeomorphism, which I haven't told you what it is yet, but it's done, it's completely constructive, and so we can characteristic sublinks to investigate how the spin structures behave. So, in fact, we can verify that this won't intertwine the spin structures, and so it indeed extends to a diffeomorphism. So in some sense, we could, once we have this diffeomorphism explicitly defined, we're in great shape. But the original reason to even think about these boundary diffeomorphisms was to investigate whether or not that Stein structure, what context structure it fills. And so we still can use Liska's classification of fillings of the standard contact structure on LP squared PQ minus 1 to also conclude that these things are diffeomorphic. And the way we can do that is that, in fact, we can arrange F so that the contact structure induced by the Stein structure on BPQ and the pullback of the one that we just produced on AMN are isotopic. And so how would you do that? Well, what you do is you use F to compare the homotopy invariants of the contact structures. So Bob Gompf has these invariants that classify two-plane fields on three manifolds. And so all we have to do is compare these things. And it turns out that as defined, these things will actually have the same invariance. And so what we can conclude is that these two contact structures are going to be homotopic. But then Kohanda proves that for tight contact structures, that this is enough because distinct isotopy classes are in distinct homotopy classes. And so once we know they're homotopic, we'll be able to say that they're actually isotopic. So in fact, this contact structure that we're getting from the Stein structure that we just cooked up on AMN actually is the standard one, which isn't too surprising, but it's still what you want to expect. So there, that's. All right, and then we just look in Liska's classification of symplectic fillings of such things, and there's only one with B2 equals 0. And so they have to agree. Okay. So, okay, how can we construct this map F? So we can do essentially what Selman was talking about yesterday by kind of going to a reference manifold. And so what we want to do is we want to think of mapping the boundary of BPQ to some linear plumbing, mapping the boundary of AMN to some linear plumbing, and seeing those as agreeing. And so how are we going to map this to a linear plumbing? Well, what I want to do is, in some sort of quotes, unwind the two handle from the one handle. And this is going to use the Euclidean algorithm, which it necessarily has to because the continued fraction expansion of p squared over pq minus 1 involves the Euclidean algorithm. Okay, so what do I mean by this? Well, what I want to do is instead of viewing this as one strand going around p times, I want to try and view it as q strands going around some number of times plus a little more. So what do I mean by that? Well, I want to write p as q times s0 plus r1. Then I want to think of this as q strands going around s0 full times. And then some of the, r1 of the remaining strands in q going around again. And in fact, we can just isotope the picture to look like this. And so we get to a picture like this. And this is a much better picture to see how to unwind this thing. Because what we can do is we can just surger the one handle, obviously damaging the four manifold, but not damaging the boundary. And then we can introduce a canceling pair to undo this twist here. And what will be left is something that looks structurally similar to BPQ with some handle attachments. So I mean, we'll have a smaller version, BQR1 plus some two handles. So okay, with that idea in mind, we can do this over and over again because inside there now we have this smaller thing, we do it again. So we have the following lemma, and for this, what we want to do is we want to just define sequences of remainders using the Euclidean algorithm. So we'll set r minus 1 to be p, r0 to be q, and then ri plus 1 we'll take to be ri minus 1 mod ri. And then we'll fix si so that this equation holds for each. And then just for bookkeeping purposes, let's fix an integer L where the last index where the remainders are strictly bigger than 1. So the next one will be 1 because we've assumed these are co-prime. So then for what we can do is we can unwind this L plus 1 times. And so what do we do? Let's say we've unwound it I times. So this here is this manifold BPQ0 I'm calling. And now what I can do is, again, I could serger this one handle and introduce a canceling pair. And then I could slide this off and isotope the picture with that same mantra in mind. And if I do that, I get back to the next one. And so you can see that each time, this attachment here is getting more and more simple. You know, it's going over the new one handle less and less times. And why is that good? Well, if we run this out to, yeah. So serger this and then open that up. And what's great is that the framings change exactly the way they should. This is sort of the fantastic thing. And then we slide this off. And so what we end up with is at some point this will essentially be an unknot itself. And so what we can get is we can get a map to the following linear plumbing. So this is what I meant by I'm not going to be looking at CPQ because I have these positive terms here. And of course, if I wanted to get to CPQ, I can blow this up and blow it down and I can get there. But this is sort of a more concise presentation, so I'm just going to stick with that. OK, so we can do the same sort of trick to AMN. Again, I can think of this as not one strand going around m plus n times, but m strands going around some number of times with a remainder. The only difference is now that I don't have that plus 1 here, then I've got a problem. I mean, it's not really a problem. It's just going to change the picture slightly. And so what we find when we do this isotopy is that, in fact, the one handle ends up linking in this way. And I'm tracing this gamma circle to see, as what I didn't say and should have, is that if we trace where mu1 goes in this, it goes to this central circle. And so what we'll see, hopefully, is that gamma also goes there. So, OK, so we do the exact same thing. Again, I'm assuming n is bigger than m. I'm going to define sequences the same way. And so rho minus 1 is n, rho 0 is m this time. And then I choose sigma i's in the same way. And then I again have some index L, which maybe we're worried that that's index is different. We can arrange it. We can arrange these choices of p and q and m and n in such a way that L will agree through those symmetries. So it's not a problem to call this L still. And then again, we get some, we can start opening this thing up at the expense, by making this, making this more simple. So it's the same trick. You serger the one handle, open this up, slide, and then isotope. This one's a little more of a pain to isotope because you sort of have to turn things around, but it works the same way. The framings work the same way. It's quite nice. So again, if we take this out to the end, we'll again get to a linear plumbing. And if we carry where this circle goes, it turns out to go there. So that's great, I guess. So then we can bring this picture back in. And yeah, so at this point, what we can do is we can actually use this as a definition for how to cook up M and N or P and Q. So like I said, Yamada uses the Euclidean algorithm. He algorithmically actually defines, you give me M and N, I'll cook up integers P minus Q and Q, and from there I can get P and Q, or vice versa. Well, what I can do instead is I can just say, OK, I can pick P and Q, and then I can just abstractly think of this picture. And then I can impose these relationships that I want the rho L's, I want rho L to equal S0, I want sigma L to equal S1, et cetera. And this gives me a system to solve, and I just work backwards. And if I solve that, once I get to rho minus 1 and rho 0, those are n and m, respectively. And if we impose that, first of all, then that tells us that these pictures will be the same. And in fact, for that choice of n and m, in fact, for that choice of p and q, it's the same definition that Yamada gives. You can actually prove that these things are equivalent. So this is not changing anything. It's just a different way of viewing this that goes. And so then this should be our map F. And so, like I said, I'd be 25 minutes. So, thank you.
Families of three manifolds, of this sort, not necessarily rational balls, but where you can use these kind of nice techniques. Families, where it just wasn't known.
Yeah, I don't know. I mean, presumably yes, but off the top of my head, I can't think of anything. I mean, there's certainly. Yeah, I mean, there's certainly other plumbings to look at and things, and for this carving technique has been huge. I mean, Selman has used it in papers as early as 77 or something, and it's a technique that seems to fly under the radar in a way, because my goal in doing this was, okay, well, put a Stein structure on it, realize that it's actually filling the standard one, and then in the process of doing that, you accidentally get yourself a diffeomorphism. I mean, that wasn't really the plan. It just sort of happens that, okay, well, and it's sort of not surprising in these so small manifolds, but at the same time, it's, I don't know.
So can you say something about the Lewis vibration structure on this BP? Search time manifold.
So, yeah, maybe not. I mean, I'm sure you can, but maybe I'm not the one to answer that in front of everybody. Yeah, I mean, I'm sure you can, and their paper, they're getting this in a fairly standard way. So I think that it's gonna. So.
How do I here? Okay, so remaining half an hour, I want to tie some loose ends, maybe give you a couple of examples using the techniques I described earlier. I should make some comment about Yesha's talk earlier. He talked about loose knot in S1 cross S2, which is the S1 direction. The way what I understand loose is in 3 dimension is a knot by isotopy. You increase its TB number. So he didn't want anything else going through that handle. So when you do this, it doesn't touch other handles. So it's clearly in S1 cross S2, when you're going around, you can increase the framing by 2. So that's, you can view that another application of carving techniques, because S1 cross B3 is a carving above B4. When you carve it, that meridian and knot becomes loose. Okay, so I wanted to, I talked about anti-corks. For lack of better word, which I'm just using this terminology, probably it's a silly terminology, but anyway, it does the job for the purposes I'm using. It's a manifold like this. M is a compact manifold, M compact. Homotope equivalent to S1. F is a diffeomorphism which extends homeomorphically inside, but it does not extend diffeomorphically. So let me, remember the corks are usually, corks are the contractible manifold. Plugs are usually homotopy S2s, and this is homotopy S1s. Those are three fundamental pieces. And let me explain how you first see this. So remember this cork, which I told you I spent all my life with, which is the Mason manifold. Yes. So there's an alpha, and this is f of alpha. So f takes involution. This is the involution here, and we draw this in a more symmetric way. Since this is a carving, this is just a two-handle. These are basically comes from the link. One is carved, the other handle attached. So you can draw them in a symmetric way. Completely symmetric way. And I guess we don't have a color choice here. By the way, this is not a color chalk, this is a pill. A yellow pill. I don't know if the lecture doesn't go well, you swallow it. So there is so the involution is like this. F, yes?
Is there some way to turn the front?
Yes. I knew this, yeah. Like this. Yeah. And then that is really the same as this one. One is a dot, the other 0. And then the alpha, this is alpha, f of alpha. I told you in corks, automorphisms, this cork map, it's important to find invariant circles that up to isotopy. You can do things with that. They are kind of the loose circles of cork. So there is one like this here, called this delta. And then the cork automorphism will take this to f of delta. This. But the difference between these two, these loops and these, you cannot isotope this to that one. But this one is, you can by an isotope, you go over that to that one. So the delta is isotopic. F delta. And this is an indication that there's a farther carving possible. So what's the picture? So there's a cork, and I have delta circle there, and then f of delta here. But since they are isotopic, I can put a color here, and I still have delta here. And I put an isotopy in the color, like this. And here, let's just make it like this. This is dot, this is 0. And delta, there's an obvious disk delta bounds. So there's an obvious disk delta bounds, D. Okay. And then when I change the dot and zeros, and the obvious disk f of delta bounds, right? If I mean, this f is nothing other than changing dot and 0. So in this case, there's a disk in here like this. So the identity map on the boundary bounds two different disks in actuality of this W. So you produced a contractible manifold and the loop on the boundary which bounds a disk in two different ways. In fact, the complements of these disks are quite different. So let me describe them to you. So the curve say delta or f of delta here. So I can carve a disk here because it's a two handle. When after I change deltas and zeros, I can carve this one. So you get a manifold like this. Okay, I carved it. So here's a carving. I remove this. Or I remove this one. Okay. I mean, I misspoke myself. I think this, I should call this f in here. This should be f of delta. And then this should be delta. Delta is the one that bounds the disk, so I use that disk. But now because of this isotopy, now it looks like f of delta bounding a disk. Okay, so I have this diffeomorphism on the boundary. Diffeomorphism on the boundary, and this diffeomorphism takes a loop to another loop, and this loop bounds a disk, and the other loop also bounds a disk. So you can carve from here and there. You end up, so you can extend. You can extend or collapse f to a diffeomorphism w minus neighborhood of this, and w minus neighborhood of f of t. I mean, call this disk, hold this f of t. Okay, so and these things they sit inside of f minus and d, and this and w minus and d. And it turns out that they are homotopical into circle. So it clearly, once you carve it, you extend, f here. So you think of it as like a little coloring here. F is defined on this color, and then you extend this color union on this handle, and then you have a color in here. You extend this color union on this handle. Clearly, you cannot extend the complement of this color union on this two handle. If you did, then F would extend. That wouldn't be cork. And yet, this is a simple connected manifold. So let me tell you why this is simple connected. Well, I mean, you can do like a slide in here. And if you do a slide in there, this picture will look like maybe I should put this yellow here. So after you carve it in here, this turns into circle with dot. And then two handles can slide over one handle. You slide this over that. Then you will see a one handle, a two handle, and this dotted, this thing. After you slit over that, you get this picture. And then you see, after you slit this, you see a chord twisting in here. In a way, the chord twisting here is ridiculously simple. There's a dot and zero. So this twist replacing this dot and zero is really replacing this dot and zero. This together is just this one. When you do chord twisting before, that extends, of course, if you change one position on one hand, two handles position, S1 cross B3, B2 cross S2. But the amazing this is, this has all the difficulty, mysticism this cork has inside this one. Why? Because when you do this change, this loop, in one case, this loop bounds a disk inside. The other case, it doesn't bound a disk inside. Like in this picture, this loop gamma, it bounds a disk, namely this disk. Because this is a two handle. But if you change, if you put a dot in here, and 0 in there, this is a violation. You cannot shade a disk. This is a one handle. But nevertheless, there's another disk this bounds on this manifold. Namely, you just do connect this one, right? I mean, you just do a slice move like this. Right? When you do slice move like this, they become like that, like this. Separate two separate disks. I'm doing a slice move like this. And now they are disjoint. They become two circles not touching the one handle, and they cap. So this guy bounds two different disks in 4-ball. In one of them exists, survives when you carve this. The other doesn't survive. I mean, the other one survives when you carve this one. But the one does not live when you change the carving. So this is the boundary. This is a 4-ball. It's a 4-ball, and there's a chord twist of 4-ball here, and there's loop on the boundary. When you B4, there's a gamma, and an f of gamma. Somehow, if you carve this one way, this survives in here, but this doesn't survive. This doesn't survive in there. But there's another disk here. When you carve that one, this doesn't survive, and this survives. This is as simple as this. And in fact, when ribbon disks, we do it with ribbon moves. So we put a dotted circle. In one case, we put a dotted circle in here. In the other case, we put a dotted circle in there. Okay. In this way, if I do the ribbon move along this, that bounds a disk in this manifold. But in this manifold, this bounds a disk when I do the ribbon move like this. So there are two ribbon moves, this unknot looking thing. And then those ribbon moves give you two ribbon disks, this bounds. And one is in this manifold, the other is the other manifold with a dot. And what I can cancel this too. I know how to cancel 1 and 2 handle. Once I cancel this, what does that ribbon look like? This one. Look like, and it looks like this. This is a ribbon knot. So I made this 1 and 2 handle disappear. All I have is ribbon knot. This is my ribbon knot, and this ribbon move is like this. And clearly, if you do a ribbon move across here, you cut this separate. They become two disjoint disks, circles. They bound disjoint disks. But what is the prohibit ribbon move? This one, that corresponds to that one. Okay. When you connect the sum like this. Okay. This is also becomes, oh, there's two twists in here. Plus two twists in here. Okay. This still becomes two circles. This is the other ribbon move, ribbon knot. So this knot, gamma, bounds two ribbons. One is that corresponds to this ribbon move. The other corresponds to that ribbon move. Okay. So this is kind of amazing thing. Here's a B4, and you have a ribbon knot. This gamma bounds two ribbon knot. They are distinct. But in fact, they are same ribbon knots. This is, again, a shocker. How can the same thing can be distinct? It's just that when you put an identity on the boundary, this ribbon knot will also look like this. The other circle, say if you put a circle delta, this f of delta, this delta, the position of this delta look completely different there. What does it mean? I mean, if you take this knot, I was shocked when I first noticed this. See, if you take this knot, you make them get them closer. This dotted, bring these 2 points together, closer. These 2 points closer. They develop exactly the same knot. You find an isotopy of this knot, taking this dotted line to that dotted line, that dotted line to this dotted line. So abstractly, they are the same ribbon, but relatively, they are different ribbons. Make sense? So this gamma bounds 2 distinct ribbon knots, but when you abstractly look at it, they are same ribbon knots.
What was the argument about getting those points
So,
together?
you know, this dotted line, what is special about this dotted line? There's a band here, right? These 2 strands of this knot very close along this dotted line, right? So, but these 2 strands, I want to bring them together, but they go far apart, right? You can force them. You bring them together, this close, and bring this together, this together, this together. You push them together, and then you develop this picture, where this gamma will look like this, and this gamma will look like apart. So there are 2 ribbon knots. Very mysteriously, they look exactly the same, but real boundary, they are different. You only see the difference when you put a dotted line here. And dotted line there, you make a ribbon knot. So the inside of ribbon, the identity, it just says that identity does not extend inside. You can carve in here the identity. Does not extend inside. So this one is B4 minus a neighborhood of this ribbon knot. The other is B4 minus f of d. But this is, in fact, secretly, I know that this thing is equal to B4 minus d. So there's no extension of identity in here, because identity on the boundary it looks different. It takes a dotted lines, different dotted lines. Okay, so I claim these are simple pi 1 z. So how do you see pi 1 z? So the pi 1 of B4 minus d is, I claim this is z, this homotopy equal to the circle. The way you see this, you have this knot. Take it bounds 2 ribbons and take the one that I can see it in this picture, this one. This is carved. And you do the following move. You can, if you have a circle with dot here and the 0 in there, and this is circle with dot, and this is diffeomorphic to all the way through here. You can cancel this 1 handle and 2 handle. The circle with dot, this carving goes this. Think of that carving. These are carved, and there's a 2 handle. This is diffeomorphic, this one, carved there. So I do that move in here. I can just do zero, a dot, and dot. Because when you cancel this 1 and 2 handle, they become the ribbon knot. You might worry about how this circle with dot going through this circle with dot. But this is a kind of ribbon circle with dot. It's OK. So you pull this, this part of the strand all the way here. You get this. So this part is pulled. Now this is just 0. And the circle with dots are these. So that's a four manifold. I claim this is pi 1 z because two handles you can homotop through each other. You just pull them apart homotopically. You're just doing homotopy in four manifold. Right? And then this picture is just this picture. This picture, the homotopically, they cancel each other, and then you have pi 1 z. Okay, so I told you that every time, so there is a really exotic manifold in here, even though it looks exactly the same, REL boundary, there's somewhere a cork hiding in there. So in fact, you can see that cork. I told you to see a cork, you need some kind of two handles to get a help from, to produce a cork, nearby cork. So let me tell you how it is done. So you have this picture. What I'm describing to you is recently announced by Ruberman, Kim, Oakley, and Melvin in their paper. They use this. So I'm explaining that part in here. So that is used to produce some examples in different contexts. So you have this thing here, and this guy bounds. Maybe I should draw this smaller. Okay, so you take the identity in here, the identity map, taking this knot to that knot. In one case, under this identity, there's a disk corresponding to that ribbon, and there's a disk corresponding to that ribbon. There are two different disks, the identity bounds. So you can go ahead. Let's see. There's this one disk. There's another disk. Okay, it's called this D plus, D minus, D1, D2. So bounding two different disks, two different. In B4. So somehow, in the complements of those disks, there's an exoticity. The identity doesn't, you can carve it, you cannot extend. But to demonstrate, to make it more visible, what you can do is you can attach a handle here. You can attach a handle. Say +1 framing, you attach a handle to these things. So then you have a two spheres. So attach handles. Handles there. And then because these are both ribbon knots and they're +1 handles, these things are each is diffeomorphic to W, before, after attach, I get a now homotopy CP2. So this thing is really a contractible manifold connected to some CP2, and this is contractible manifold connected to some CP2. What is that? You can just take a tubular neighborhood of this, a sphere of self-intersection +1. It's just a punctured CP2. complement is a contractible manifold. So I know that the complements are this thing, this complement of disk and that complement of disk, okay, from the description of cork. But I want to see this more concretely in this concept. I mean, I know there are different real boundary. So what I can do is I can blow this S2, CP1, and blow this as CP1. So what I can do is blow down S2, blow down S1. So you get a contractile manifold. I tell you what contractile manifold you get. It's going to be just this one. This. And this is another cork. We call this cork. And nowadays, corks have names. This is a W1 bar cork. This one, the usual Mason manifold, W1 cork. And this cork is called, we call it positron because it is used to make manifold Stein when blowing this one down, make it kind of handles positive. So they appear naturally. In fact, they appear E1. If you take a Dogdachev surface, you do PQ. This is exotic. This is exotic E1. And there's a usual E1, which is, you know, that's CP2 blown up 9 times. Okay. Inside of it, you can see W1 bar cork. Inside of it, you see W1 bar cork. And then you go from here to here to cork twist. I wrote a paper on Dogdachev surface. This is one of the things in that paper. So this is an exotic copy of E1. You can locate this cork. The cork twist, it becomes standard. And that cork is exactly this one. So when I blow this one down, I know they are different. I blow down different spheres. So change of position on the nuts on the boundary, the position change. The most dramatic ones you can see, if you take a nut in here, so theta, it goes to here. Call this f of theta. So when I blow it down, this identity becomes a map like this. This map taking this theta to f of theta. So this identity becomes a cork twist. So when you attach handles to this anti-cork, and then you blow down handles, corks pop out. So so this shows anti-corks related to corks, and they are also, you can also make examples when you translate plug to a cork. So this is an example in the presence of two handle, this anti-cork turned into a cork. Any questions? Yes.
Is there no diffeomorphism between the sliced disc? Are the sliced disc complements diffeomorphism through a different map, or there's just no?
Complements of this sliced disc are the same. It's just that there is an abstractly they are same, just like cork. Cork is the same, WW. But when you have a map on the boundary, which doesn't extend inside. So how should I explain? So that's a cork. They are same. There's an F which doesn't extend inside diffeomorphically, but it extends homeomorphically. Suppose you take this homeomorphism, you pull back the smooth structure in here. So you get, then with that smooth structure, they are diffeomorphic, extending this F. So that's a different smooth structure, real boundary. So it's a similar phenomenon, it's the knot complement, ribbon knot complement. I mean, how can I see this? When think of this as some kind of comet, and you are standing in here, the completely symmetric on the the boundaries. There are two mountains in there, okay, and then you are standing in here, okay. But somehow in this under these two mountains, there's a kind of a gold mine in here. Okay. And then when you do this, when you do F, this guy goes to here. Okay. Yeah. So I mean, there's a symmetry on the boundary. If you are on the boundary, there are two mountains. Either you are here or there. You look like the same place, except one of the mountains has a gold mine underneath. The other doesn't. You don't see it on the boundary. So when you do the involution, and this guy now goes in here with the things with a gold mine underneath. Okay, but if you the person living on the planet, it will like nothing change. It's living in the same place. Same with this the ribbon complements, and it becomes very clear in here when I blow down to the ribbon complements. There's this cork happens.
Isotopic?
They are not isotopic. Of course, they are not isotopic, but abstractly they are the same. The two ribbon disk, there's a ribbon disk, they are exactly the same as this, but the identity doesn't extend inside. There's no isotopy rel boundary. If you fix boundary identity, so I'm on the boundary, I fixed the ribbon nut, it has two ribbon disks, they're not isotopic to each other. But abstractly, they are the same ribbon. It's hard to believe these things when you first see these things. You know, it is disappointment after disappointment, but somehow you feel good. It explains some things very weird, perverted way. So the other thing, looks like I'm almost out of time. I was going to explain some the infinite filling of contact manifolds. If you have two contact tree manifolds, and this is a theorem I proved with Yasui, that you can find infinitely many different Stein structure and fillings of this contact structure. And that gives you some of the techniques to distinguish exoticness by using a junction equality. But it looks like now I'm out of time now, right? Okay, can I go 10 more minutes? You sure? Okay. So now I will describe this theorem I proved with Yasui. There it is related because recently I'm thinking there could be infinite order corks, but it's very related to the technique. And maybe I should tell you the technique. So here's a theorem with Yasui. XP, so let XP is this four manifold. This is very small. Burak mentioned this result. He said this manifold is very small. You can see it's very small. It's like this. P twist in here, P minus 3, and take minus 2. Let me make one handle with color. Okay, and then this is 0. Okay, XPs, boundaries XPs are the same contact homology spheres. And as P going to infinity, they are the same thing on the boundary, they are same contact homology spheres. As P going to infinity, XPs are not diffeomorphic to. You get XPs realize infinitely many diffeomorphism types. Yet each XP is a Stein manifold. Contact homology spheres, you call this like YC. A Stein manifold filling in YC. So you have a fixed contact tree manifold, which is in fact homology sphere. There are infinitely many Stein manifolds fillings, and this Stein manifolds, as parameter goes to infinity, there are infinitely many of them not diffeomorphic to each other. They are exotic copies of each other. This kind of what you want to do if you want to find infinite order quark. You want to, this is homotopy equivalent to V2, xp is equal to 2. You want to do maybe this to be 0, contractible manifold. And diffeomorphism, they are diffeomorphic to each other. In fact, they realize, and XPs are, all XPs are homeomorphic to each other. So the exotic means that they are homeomorphic but not diffeomorphic to each other. And then you go to, there's a infinite order diffeomorphism on the boundary. Infinite order diffeomorphism. That diffeomorphism obtained, so this is a circle with dot. It's illegal to blow up. But I'm describing a diffeomorphism on the boundary. Blow up, slide it, it will come in here. And then blow it down. Blow up, slide, blow down. Blow up, slide, blow down. So that's a diffeomorphism on the boundary. So this diffeomorphism is real locally is this. So there's a torus in here, T2 cross D2. Where's that torus? Let me draw it like this so that you'll see the T2 cross D2. If you cancel these two, you put the one left of it. But these two yellows of here and this one is T2 cross D2. You see that, T2 cross D2. And that's a T2 cross D2. Yellows are one handles, so this, I draw it like this intentionally. Okay, and this one. And that's 0. And the diffeomorphism I'm describing to you is blow up here, blow up, slide, come in here, blow down. So if you have a dotted circle in here, just to show that the circle in here, alpha and beta. When you do this diffeomorphism, you get the dotted circles become P2 is here and minus P2 is there. So this is alpha, beta, and this is f of alpha, f of beta. This operation done P times. In fact, this turns out to be exactly Luttinger surgery done with Luttinger surgery. Done P times. At the times we didn't understand Luttinger surgery well. We somehow tried to explain this by log transform. And then we had to go through a lot of difficulty somehow explain this in terms of log 1 transform. But when I look at Luttinger surgery, I studied it carefully. This is exactly Luttinger surgery. You do P times. And because of this, these manifolds are Stein. You can see that they are Stein. You can, XPs are Stein. And they're very easy because they are, you draw them with diagrams like this, then you recognize them. So this, they look like this. So that's that minus 2, TB minus 1 in here. So this minus 2 curve. And then you have that's that this one, 0. And then you have another curve. And there's a p minus 1 strands. And this curve is let's give names. Call this alpha curve. This is beta curve. This is T, torus curve. So this that thing is a beta curve, and that's the alpha curve here, and this is a torus curve there. I circled, and the Legendrian position, and the 0 surgery in here, -2 surgery in here, minus P minus 3 surgery makes it Stein manifold. This is Stein manifold there, and then you you are doing a Luttinger surgery inside of Stein manifold. So that's the reason that that survives. The Stein structure survives inside, roughly. Okay. And the proof is basically adjunction equality. There are two kinds of adjunction equality. One about the homology classes, the other about the properly embedded disks, say contractible manifolds. You basically make a homology class. Call this homology class. You see the handle alpha goes p times like this over one handle. So you do alpha minus p times beta. Then it is no longer going through one handle, so it's homologous 0 loop. So we call this theta. So that's a handle. Theta square is alpha square is minus p minus 3. So that this was minus p minus 3 plus p square minus 2 p square. So this is some odd number 2k. If you this is a homology class, and you can add this homology class copies of T. T is just a null homologous curve. So you plus k times T. So call this homology class C. Okay, and this is self-intersection 0 homology class. And the adjunction equality, when you attach these handles, it says that 2G minus 2. This is the genus. G is the genus of the surface. Surface realizing homology class. So this should be greater than or equal to C square. So this is 0 plus rotational number, absolute value of rotational number of this Chern class. Rotational number of this we can very easily calculate. This is 1. This is 0. So R is here 0. This is 1. And this is 1. This is 1. But you are adding this p times that. So that is going to be like 1 plus minus p. This calculation. And the right-hand side goes to infinity. Is p going to infinity? So when you take p large, the homology class representing the genus of surface representing this homology class going infinity. So they cannot be diffeomorphic very large. So you want to do the same thing with a manifold beta number 0. So in that case, there's an adjunction equality where you have the 2G minus 1 in here. That's the TB of the knot. It bounds. And there's an R in here. So you want to choose that knot and TB so that this will go to infinity. Okay. I thought I did this like last week, and I'm still having difficulty some calculations. I'm trying to convince Yasui my calculation, but I'm failing by 1 so far. But that's just a very fresh calculation. It might yet work, or you don't know. And from let me tell you at least the manifold I'm thinking about this infinite cork. There's an amazing diffeomorphism a contractible manifold has. Corks have order 2 diffeomorphism. He's taking a contractible manifold like this. There's a ribbon knot. You put a dot in here. Okay? Then you put any handle, anything in here. Here's a -1. That's a Stein manifold. We can prove that this thing is a Stein manifold. And there's the infinite order diffeomorphism, because you see this, you take this dotted loop in here. gamma. So what you do is you hold with your hands. You give 360 rotations to this. That corresponds to blow up here, slide, blow down. Blow up here, slide, blow down. Blowing up on circle with that is illegal, you know. I'm describing diffeomorphism on the boundary. When you do this, there's an n twist in here you create, and minus n twist in there. And this gamma, so f, you do this n times, composition of f n times, you get a new curve, gamma n. So when you draw this time picture, handled by the picture of this, and then you apply a junction inequality to gamma n. Now this gamma n goes through one handles like crazy. When n equal to 0, it looks like this. This manifold is that manifold. It's a ribbon complement. And that gamma 0 is this one. As you see, gamma 0 bounds a disk. But when you do this twisting by hand, you put an n twist here and minus n twist there. Now it's badly going through one handles. It's gaining in Thurston-Bennington and the rotation number. And when you have a contractible manifold, and the ribbon, the disk, it bounds, genus G. So you have 2G minus 1. I mean, of this greater equal to, you have TB of K. K is here, plus rotational K. So in our case, we want to use gamma n in here. And you want to prove that this goes to infinity. Is n going to infinity. So the genus go to infinity. That's a junction inequality for contractible manifolds, contractible time manifolds. That's something I proved with Matvey many years ago, right after Taubes, Szabo, Morgan, Kronheimer, Moravka proved their junction inequality for closed manifolds. We needed to use this time manifolds. We did this. In fact, shortly after this, Moravka and Rollin generalized this for n-symplectic manifold. So there's an injection inequality for properly embedded surfaces in time manifold or any symplectic manifold boundary or exact symplectic manifold. And it says that the genus bound by TB plus, actually there's a framing here. I'm just lying you slightly. And then the rotation number in there. So you want to, every time you apply this diffeomorphism just pumps up air inside, but in the boundary you don't see it. And then gamma gets more and more tangled like this. And then you want to violate this. But I seem to not yet have the proper proof of this. I thought I have the proof. I wrote it down, sent it to people. But I'm not sure anymore. Any questions? I guess I went over time. 15 minutes.
I'm sorry, I'm just trying to understand that it means to be an infinite order court.
Infinite order court means a time manifold, a diffeomorphism on the boundary, which doesn't extend inside the diffeomorphism inside, but extends homeomorphism inside. And that homeomorphism gives you a new smooth structure on W. So W, take any homeomorphism in here, homeomorphism. This gives you a new smooth structure. This is a pullback smooth structure. By F. So homeomorphism will pull back smooth structure. Now you want to you want to look at these things. F compose F compose F compose F. You do like F to the n, right? And then you extend them, and then you pull back smooth structure should be different. That's the quickest way I can tell the infinite order court. There are different ways to describe to you. So all the compositions extend homeomorphically. This homeomorphism will pull back a different smooth structure. That's what we are looking for. Because it's order 2, it's the involution. All the corks we've been using, corks, plugs, and somehow they come from the construction as order 2. The two.
I thought that the definition of cork said you wanted an involution, or is that?
Yeah, that was the definition we did. We formalized this with Yasui. We wrote a paper. We thought it's sufficient, but now we are not sure anymore. After this example, for instance, you can think of this kind of fat cork, infinite order. It has just beta number 2. It just doesn't. So, any more questions?
Yes.
Yeah, there's an algorithm, Burak and I have. You can put this algorithm and get a canonical ledger structures on this.
Like genus? Like,
I don't know, you can do it. I mean, you just put them, every crossing you put 45-degree rotation, put in square position. You remember I draw that diagram, and then you do PQ torus knot with the one handles cork structure of B4 and the S1 cross B3s, and then they turn out to be the Dane twist on those. Left chest fibrillation structure 4-ball or connected sum of S1 cross B3s. So you can do it in 10 minutes.
Interesting to say about like what this involution is doing to the open book decomposition.
I think this is still a young subject, even though it's going on many years. Really, we didn't study it carefully. There's tons of problems like this. How this involution, in some examples you can do it. In some examples we worked, but I think there's some general way to approach this. There should be. Thank you.